Not streaming. All right, can everyone hear me?
Yes.
I can turn on the mic if need be, but if this is good, then we'll go with this.
Fine.
All right, great. Thank you all for coming to today's LLVM seminar. I'm TV Shardle. I'm one of the facilitators for the seminar. And today I'll be talking a bit about some research work we've been doing in the group called Tapir. This work is focused on embedding recursive fork-join parallelism into LLVM's intermediate representation. We've been working on this project for a couple of years now. Most of this work is a collaboration between myself, Billy Moses, and Charles Iserson, all in the SuperTech group, although there will be parts of this presentation that are collaborations with others, and I'll talk about them when we get to those parts. But to start everything off, I want to show you an example of the problem that Tapir aims to solve. So in this example, we have a small snippet of very simple C code. This C code aims to normalize a vector. It takes an input vector, a size, and an output vector. And all this code does is it loops through the elements of the input vector, divides each one by the norm of the input vector, which it computes via that call to norm, and it stores the result into the output vector. Pretty straightforward. We can compile this code, run it, and see how well it performs. And when we test this code on a random vector of 64 million elements on a fairly easily accessible Amazon AWS compute node, we see that it runs in about 0.3 seconds. Now, for some purposes, we might want to speed up this code, and we may want to speed it up by using parallel processors that are ubiquitous on today's modern machines. So how would we parallelize this code? Well, fortunately, there are a lot of technologies out there today, a lot of parallel programming technologies that make this a pretty simple task. One such technology is the Silk programming language technology. And what Silk lets you do is just transform that for loop into a Silk for loop. The observation here is that each iteration of the original for loop was independent. And so all of those iterations could be done in parallel. And if we use Silk, we transform that loop, and the Silk for loop here simply designates that all iterations can be executed in parallel. Great. So we've now parallelized this code. We expect it to run faster when we run it on a modern multi-core machine. In fact, our test machine from before had 18 cores in it. So let's give it a go. We run this code, and we see that compared to the original running time of 0.3 seconds, the new code on 18 cores runs in about 3 minutes, which is slower. Now, there are a lot of reasons why parallel code might run slower than serial code. With a bit of investigative work, what we discover is that when we run this code on just one processor, we find that it runs in close to 40 minutes. And so we actually see that the code does achieve parallel speed up on 18 cores, but the problem is that this code has what we call terrible work efficiency. If we take the ratio of the running time of the original serial code divided by the single core running time of the parallel code, that's what we call the work efficiency, and in that case, the value is around 1 in 8,300. That means in an ideal scenario, if we had 8,300 processors, we could get this parallel code to match the performance of the serial code. And that's in an ideal scenario. Generally speaking, we're not going to achieve that level of speed up. This is just a big problem. So how did this happen? Why is this parallel code running so much slower than the serial code? Well, as you might have guessed, by virtue of the fact that you're at the LLVM seminar, the problem is the compiler. And for the quickest and highest level overview of the LLVM compiler that I can certainly give, here is the LLVM compilation pipeline in 7 boxes, plus some annotations. So what LLVM does, it takes in C code as input, and it feeds that to the Clang front end. That front end generates the intermediate representation of the code in LLVM, which is aptly named LLVM IR. LLVM IR is then fed to the middle end optimizer within LLVM. That performs analyses and optimizations on the code, produces an optimized LLVM IR, which is finally given to the code generator to produce a machine code executable. Now, if we give this LLVM compiler the original serial C code, what we find is that the optimizer in the middle does a pretty important transformation. It observes that the call to norm inside that loop produces the same value in every single iteration. So why call norm over and over again when instead it can just call norm once outside of the loop, store the result in a temporary, and use that temporary inside of the loop. That is a simple optimization for the compiler to do. It in fact does it, and it nets some amount of speed up. That's the story with serial code. What's the story with parallel code? Well, the good news is that the parallel compilation pipeline is pretty similar to the serial compilation pipeline. Here below the LLVM pipeline, we have the compiler pipeline for the Silk plus LLVM compiler, illustrated at a very high level. This takes in Silk code. It sends it to a slightly modified front end, which for our purposes we'll call pclang. That generates LLVM IR, sends it to the optimizer. The optimized IR goes to CodeGen, produces an executable. Now the important thing to note in this pipeline is in fact the front end, that pclang front end, deals with all of the parallel language constructs within LLVM. None of those constructs look like anything interesting in the IR. Well, what do they look like in the IR? How does pclang actually work? Well, we can take a look at it, and I'm just going to show you C pseudocode because looking at the actual LLVM for this is kind of a mess. But essentially what happens, if we give it this simple normalized code, parallelized using a Silk 4, what the pclang front end gives us is spiritually the same as what's shown on the bottom. And there's some complexity to this, but I'll walk you through it. So the first thing that we see here is that in our normalized function, we don't have a loop. What we have instead is a call to the Silk RTS Silk 4 function, which takes a bunch of arguments, one of which is this struct argument, some other values, and then a pointer to another function which has appeared out of nowhere. That was, in fact, generated by the pclang front end. That helper function, called normalize helper in this case, parses the arguments passed into it, and then it runs the body of the loop. Now that's all good and fine. This is correct code in this case, but there's a problem here. When the optimizer comes along and it takes a look at, it looks at this code, it sees this call to norm inside of this normalize helper function, but it is hopeless at recognizing that this call to norm, in fact, occurs within a parallel loop, and in fact can be moved outside of that parallel loop. There's no loop in this code whatsoever, not as far as the compiler can see. There's just an opaque function call which takes a pointer to some other function which has the body of the loop. So existing optimizations they have no hope at all to move this call to norm out of the loop. Now that, I'm sorry to tell you, was a relatively simple example. If we take a look at a slightly more complicated piece of parallel code, here we have everyone's favorite exponential time Fibonacci computation parallelized using Silk. If we feed that code to the parallel-clang front end, what we get in C pseudocode terms is something like what's shown on the right. And you don't have to understand all of this for the sake of the presentation. What we see here is just a jumble of stuff. There's a new local variable within the fib function. There are some opaque calls that could modify that variable. There are some set jumps. There are checks on flags. There's a new helper function, which also has some more opaque calls to a runtime system. Suffice to say that the compiler has a tough time optimizing this fib routine around all of these opaque function calls. So that's the state of affairs. It has some problems. The compiler struggles with it. So what could we do about it? Well, a very simple idea is to say, what if we take parallelism and we embed that concept inside the IR of the compiler? So rather than go with the Silk plus LLVM pipeline, where the pclang front end deals with all of the parallel language constructs, what if instead we built a pipeline where that front end generated some parallel variant of LLVM IR, And that was fed to the optimizer in order to produce optimized LLVM IR. And somehow that parallel LLVM IR encoded all the parallelism for optimization. That'd be great. That would seem to allow us to solve this problem. Now, this idea is not a new idea. In fact, it's a pretty old idea, dating at least back to the early 90s. It might date back further. If you know of earlier references, please let me know. But there have been a lot of attempts over the past several decades to embed some representation of parallelism into a compiler's intermediate representation and allow compilers to optimize parallel code. These attempts have been made both in academic literature with parallel precedence graphs and parallel furrow graphs, concurrent SSA, parallel program graphs, as well as in industrial settings, as you can see from the references to LLVM dev threads. So a lot of people have looked at this problem. A lot of people have tried different approaches to solving this problem. And when we came along and said we want to try to put parallelism into a compiler's IR, well, we told this idea to the LLVM community back in 2015, and this was their response. Introducing parallelism into a so far sequential IR will cause severe breakage and headaches. Parallelism is invasive by nature and would have to influence most optimizations. It is not an easy problem. Defining a parallel IR with first-class parallelism is a research topic. Actually, we found that one pretty encouraging, given that we're a research group. And these communications continued over the subsequent years. In 2016 and 2017, we saw comments like there are a lot of information needs to be represented in the IR for backend transformations for OpenMP. And if you want to support all parallel programming features in the IR, a lot of lines of code would probably have to be modified in LLVM. And this is not a naive view on the problem. Like I said before, a lot of people have looked at this problem. They've struggled with it over decades. So this is refined wisdom by many folks who have tried to tackle the parallelism in the compiler problem. Nevertheless, undeterred, we went ahead and gave it our best shot. And what we came up with is something called Tapir, which ostensibly stands for Task-Based Asymmetric Parallel IR. It also happens to be the name of that funny animal on the slide, and that's kind of a thing in computer science. So yeah, we went with it. And Tapir fulfills that role of the PLLVM IR box that we saw on the previous slide. The Tapir LLVM pipeline takes in, for instance, Silk code, transforms it through the P-Clang frontend into Tapir, and optimizations run on that before finally being generated into executable machine code. But here's the thing about Tapir. What Tapir does is make a minimal modification to LLVM, adding just 3 instructions to LLVM IR to encode recursive fork-join parallelism. And it does so in such a way that with few changes to LLVM's existing optimizations and analyses, those passes now work on parallel code. Now, what do I mean by few changes? Well, here's a breakdown of the lines of code that we changed in order to implement Tapir LLVM in LLVM 6. And we've broken down the lines of code within LLVM 6 into a few high-level categories. There's the core middle-end functionality, which basically implements the analyses and optimizations in the middle end. There are a lot of lines of code dedicated to regression tests, and there are lines of code dedicated to other tasks as well, such as utility tasks. And the breakdown of lines of code changed for Tapir is largely as follows. We only had to modify, of the 500,000 lines of code in the core middle end of LLVM, we had to modify less than 3,000 lines. We needed to modify about 1,000 lines just to put in the instructions and renumber some explicitly enumerated lists. We had to modify another 500 lines or so in order to ensure that LLVM properly modeled the memory behavior around the new instructions. We had to modify a little less than 1,500 lines in total to get optimizations to understand and properly optimize around Tapir code. And there were 17 lines of other changes, I believe, to LLVM's code generation facility, largely to address some bugs that we exposed in the course of this project. We also added some of our own regression tests. We introduced some new code to actually lower parallelism into parallel runtime calls so we could generate executables that in fact run in parallel. We added about 3,000 lines we added was dedicated to supporting parallel tools such as race detectors or scalability analyzers. And there were a few other changes that we made to the code base. So all in all, of the 6 million lines of code within LLVM 6.0, we modified about 18,000. Now, that's a pretty significant number of lines of code. You wouldn't want to sit down and code review a patch of 18,000 lines changed. But this is far from a dramatic rewrite of the whole compiler to introduce parallelism. This is a pretty small change compared to everything else that's going on. And once again, only 3,000 lines were changed in LLVM's heart, its core middle-end functionality. Now, after making those changes in order to implement Tapir, what do we get as a result? Well, if we come back to that original example and we take a look at this normalized routine, if we feed this normalized code to Tapir and we run it on the same test input, we see that the new single core running time when this is compiled with Tapir LLVM is 0.32 seconds, just ever so slightly slower than the original running time of the serial code. And on 18 cores, we in fact see that Tapir gets some parallel speedup. So what we've seen is that Tapir allows this code to achieve great work efficiency. And in fact, that call to norm is hoisted outside of the parallel loop, as we would expect. But we didn't implement Tapir just to get this one example up and running, although it was pretty satisfying to do so. And in fact, we've tested Tapir on a variety of Silk benchmarks. I believe this is 35 benchmarks in total for the latest collection of Tapir performance results. And what we did is we compared Tapir against a reference compiler, which we designed to be as similar to Tapir in every way except for the Tapir part. So the same optimizations are being performed in the same order, same level of engineering, so on and so forth. And what we did is we took each of these benchmarks and we compiled it using reference, and we compiled it using Tapir LLVM, and we looked at the work efficiency of each of those executables compared to the serial version of those parallel programs. And we applied it on this plot. And what do we see? Well, across these benchmarks, we see that reference achieves okay work efficiency on several. A lot of those are benchmarks from the problem-based benchmark suite, which have been fairly extensively engineered. But it is losing out on work efficiency in several cases, including some Silk 5 benchmarks, some problem-based benchmark suite codes, and as well as some Intel codes. But that's the story with reference. When we compile each of these codes with Tapir and we look at the work efficiency, here's what we find. Across the board, Tapir is achieving, I think in almost all benchmarks, maybe all but 3, Tapir is achieving better work efficiency than the reference compiler. And moreover, in a lot of cases, Tapir is achieving work efficiency that's close to the ideal work efficiency. When you take that ratio, you would expect that in theory, you shouldn't get work efficiency better than 1. In practice, well, compilers are full of heuristics and weird things can happen. And so occasionally we get a data point that's, in fact, above that ideal work efficiency line. And speaking to some of the other benchmarks, in fact, we looked at what was going on with a few of the benchmarks where Tapir was underperforming. In many cases, it's just measurement noise. If we run it in a slightly different environment, we see an inversion, and Tapir, in fact, outperforms. In the case of N queens, that one's pretty consistent, and it turns out that when Tapir is in place, the LLVM compiler sees another loop later on and decides that it's profitable to vectorize that loop when, in fact, it's not. And so, once again, those heuristics end up being to our ever so slight detriment. So overall, we're seeing that Tapir achieves higher work efficiency with improvements ranging from 5% to 25% on about a third of the benchmarks. And in only a handful of benchmarks is Tapir underperforming. Now, we've, in fact, explored applications of Tapir in other settings more recently. And just over the past few months, we looked at embedding Tapir into Google's TensorFlow machine learning framework. TensorFlow, in fact, has a compiler inside of it, and that compiler is based on LLVM. The compiler is called XLA for Accelerated Linear Algebra. And that compiler pipeline is a bit more complicated. You can think of it as having two levels of IR. There's a high-level IR, which is the first thing that the compiler translates the input TensorFlow graph into. And some high-level optimizations are performed on that IR before it ultimately emits LLVM IR code, which goes to the ordinary LLVM compilation pipeline. And what we decided to explore was how Tapir would perform if instead of targeting LLVM, we targeted Tapir. We had to generate parallel code, and in particular, simple parallel code written in Tapir form, and fed that into the Tapir compiler. And at a high level, here's what we found. We've tested this thus far on 4 different benchmark machine learning networks, all compiled using XLA. And we tested it on 4 different hardware architectures. And I won't linger on this slide too long, but across the board, we're seeing that the Tapir XLA compiler, with its relatively simple compilation strategy, in fact, outperforms the original XLA compiler. And depending on the actual hardware and the benchmark, the performance improvement can be quite significant. I think the geometric mean multiplicative speedups range between 30% and 100%, which is quite high for anything related to compiler stuff. So I just want to share those recent results with you. For the rest of this talk, I want to give you a high-level overview of Tapir itself and how it extends LLVM IR. And then we will have a small tutorial on how to use Tapir to introduce parallelism into some language. And of course, this being LLVM, we will introduce parallelism into the Kaleidoscope language with all of its great features, as we'll see. And then I want to close with a word about debugging Tapir. Before I continue, any questions?
Have you, with the Silk benchmarks, if you try bigger workloads, is there the same sort of discrepancy?
These benchmarks?
I meant like earlier with the normalize and the vector. Is Silk still doing, I guess, not smart things where it can't?
Oh, I see. With the normalize, this one.
Yeah.
Yeah, so what's happening here is that the norm routine is a linear time routine. And when the norm routine is left inside of the parallel loop, the overall complexity of this code is quadratic. When it's hoisted outside of the parallel loop, it ends up being linear. Don't expect asymptotic improvements every day from your compiler. There's a reason why these improvements, as impressive as they are in the range of 5 to 25%, not 8,300. But this is a particularly potent example of how compiler optimizations can fail on parallel code and what that can mean in terms of the performance. But just to give you a sense, that 8,300 number is roughly speaking the square root of 64 million, and that comes from this difference in quadratic versus linear behavior. So the math, in fact, checks out. Anyway, but great question. Anything else? Okay, so let's dive right into it. First, let me start with a little bit of almost certainly unnecessary background on LLVM IR. To understand this portion of the talk, we only need a high-level understanding of how LLVM IR works. And basically, all we need to understand is that LLVM represents each function in the program using a control flow graph, or as we'll say, CFG. That control flow graph has a few components. Each node of the control flow graph is a basic block, which contains a sequence of instructions such that control can only enter the beginning of the basic block, and it can only leave from the end of the basic block. And in order to make this a graph, the nodes of the control flow graph are connected via control flow edges. Now, there's an implicit invariant that LLVM optimizations assume about a control flow graph. Namely, whenever you have a basic block with multiple incoming edges, it's assumed that when this basic block is executed, control comes from just one of the many predecessors of that basic block. If you re-execute the basic block, perhaps you come in from another predecessor, but each time you execute it, you're just coming from one predecessor. That's not an explicit assumption coded up in LLVM. It's just implicit throughout the design of compilers. Does that make some sense? Any questions about that? You'll see in a second why I'm calling out this particular assumption. But first, let me give a little bit of background on the other major component that we're concerned with today, and that has to do with parallelism, or as we'll refer to it, task parallelism. So Tapir is focused on task parallelism, which grants permission for parallel execution, but does not demand parallel execution. And we can see an example of this from some simple Silk code. Here, once again, we have our exponential time fib computation, parallelized using two Silk keywords, Silk spawn and Silk sync. And what these keywords mean, in the Silk spawn case, is that the spawn function is allowed to execute in parallel with the parent caller, the continuation of that function call. It's not required to execute in parallel, but parallel execution is allowed. If there are processors on the system available that have nothing better to do, they can choose to start executing the subroutine in parallel. The Silk sync is the complement of the Silk spawn, and essentially that means that control is not allowed to pass this point until all spawn computations within the function have returned. So that's the basic model. We've already seen the third Silk keyword, Silk 4. That just allows all the iterations of a loop to execute in parallel, so I won't recap that here. Now, how do we represent this? How might we represent this using some sort of parallel IR? Well, a lot of previous attempts at developing parallel IRs have aimed to model parallel tasks in a program in some symmetric fashion. So in our fib code, we have these two recursive calls to fib of n-1 and fib of n-2 respectively. And an intuitive thing to do is to say, let's take these recursive calls and let's put them into separate basic blocks. Let's have a fork construct of some sort above those two calls with two outgoing edges. And let's have some join construct where those two parallel invocations will come back together. This is a pretty straightforward and intuitive idea, but it turns out that this idea has some problems. And in particular, a lot of those problems arise due to that join construct. That basic block, which starts with a join, breaks a bunch of implicit assumptions about the control flow graph representing the function. And in particular, that join, if you think about it, it means that all of the predecessors of the basic block must have executed before you get to that point, before you cross that join. And that's very different from how other basic blocks in the control flow graph work. Like we said before, if you have multiple incoming edges, the typical assumption is that control only enters from one of those edges. But here, the join block ends up being astonishingly weird in that there's some kind of union over the incoming edges in order to reason about control flow. And that trips up the compiler. That tends to require a lot of changes to the compiler to accommodate. So what does Tapir do? Tapir doesn't, in fact, do this. Instead, Tapir chooses to represent parallel tasks in an asymmetric fashion. So on this slide that I'm showing, we have the symmetric CFG we saw previously on the left, and the Tapir CFG on the right. And what we can see here is that, yes, indeed, the two recursive calls to fib still end up in different basic blocks. But we don't have the same kind of join point. Instead, what we have is this control flow edge that runs from the end of one of the basic blocks to the beginning of the other basic block. It actually connects one of the tasks to the continuation, or to the other task, rather than to the join point. So that's different from how the symmetric CFG works. What's the reason behind that edge? Well, intuitively, this edge models what we call the serial projection of this parallel program. if I were to run this parallel program using just one processor, there is an order in which all of the tasks would execute. And that order, in fact, follows this weird-looking edge. We can compute the serial projection from the Tapir CFG as a simple static transformation just by replacing the detach, reattach, and sync constructs into more familiar serial constructs. The detach becomes a branch to the detached block. The reattach becomes a branch to its destination. And the sync in this figure becomes a no-op. So that's what we call the serial projection. This form also admits a pretty slick representation of parallel loops. And in particular, it allows Tapir to represent parallel loops in a very similar fashion to how LLVM normally represents serial loops. So here on the left, we have a mock-up CFG for the normalized routine that we've seen in the previous section. And on the right, we have the Tapir version of this parallel normalized routine. And the main change that we see here, all the components of that loop body are still around, but the body of the loop itself has been moved into its own basic block, which is sandwiched between one of these detach and reattach instruction pairs that we get from Tapir. And because this parallel loop representation is so similar to the serial loop representation, Tapir is able to, the compiler is able to analyze the parallel loop representation very similarly to how it analyzes ordinary serial loops. In fact, more generally, a lot of the compiler is able to reason about the Tapir CFG as just a minor change compared to the CFG of the Tapir program's serial projection. And if we take a look at this basic block where we've got this funny edge moving from the detached task to its continuation, and we think about what those edges mean, the meaning of those multiple incoming edges is very similar to what we get whenever there are whenever we have other cases of multiple predecessors to a single basic block. In particular, the compiler is pretty much allowed to assume that control enters this basic block from just one predecessor. That's sufficient for a lot of the compiler analyses and optimizations, and thus many parts of the compiler can apply standard implicit assumptions about what has to execute before that basic block. So what do we ultimately change in order to adapt existing analyses and optimizations in LLVM to handle Tapir? Well, I've been saying not much. Here's some numbers to be a little bit more concrete. If we consider dominator analysis, a fundamental analysis within LLVM, that required no changes whatsoever. Dominator analysis just worked as it was. Similarly, if we look at common subexpression elimination, that optimization in LLVM also required no change. It was able to reason about subexpressions in Tapir CFGs and hoist them out appropriately. There were some optimizations that required change. The loop invariant code motion optimization, which was responsible for hoisting that norm call out of the parallel loop, that required ultimately a 53-line change. Tail recursion elimination, we made a 106-line change there, and that was not because it didn't work on parallel code per se, but we wanted tail recursion elimination to eliminate recursive tail calls that arose in parallel subroutines, because it turns out that's perfectly legal. And so enabling tail recursion elimination to do that extra optimization, that's what required the 106-line change. And in addition, Tapir, we found enabled new parallel optimizations, such as redundant synchronization elimination or empty task elimination, which we were able to implement using within 236 lines of modification to the simplify CFG pass. Here's a more explicit breakdown of all the changes that we made. I won't go through this in too much detail. I'll just call out a couple of the highlights. At the top here, we see that most of the lines of code changed in optimizations occurred within shared utility functions, which are called throughout the LLVM optimizer to reason about or modify the control flow graph. I mentioned the 236 lines of change to CFG simplification to implement those new optimizations. tail recursion elimination is the highest percentage change of all of these passes. And overall, the amount of change that we made amounted to less than 1,500 lines of the nearly 200,000 lines of LLVM 6.0 dedicated to 60 or 70 optimization passes. So that's the high-level overview of Tapir. Any questions about that before we move on? All right. So a lot of this has been research talk so far, and I hope you've enjoyed that part. But as promised, there is a bit of a tutorial, because you can, in fact, obtain Tapir yourself and play around with it. And what we'll see today is a short tutorial on how to use Tapir to add parallelism to a very simple language. And the language of choice will be the Kaleidoscope language used in LLVM's Kaleidoscope tutorial to introduce the basic concepts of LLVM to newcomers. And before I continue, just a quick shout out to Daniela in the back there for helping out with the creation of this tutorial. So, as I mentioned before, you can try out Tapir LLVM yourself. You can download Tapir LLVM and its associated front end and package of tools from the web. The basic instructions for how to build Tapir LLVM from source can be found online at silk.mit.edu/download, partway down the page. If you want to follow along with this particular tutorial, I recommend checking out the XLA 8 branch, which is still a work in progress branch, but is quickly gaining stability. And that branch exists in all three of the main repositories for Tapir. And once you've checked out that code, you can use that copy of LLVM to compile Silk programs using Tapir by passing the additional fsilk plus flag to Clang. You can also get Clang to emit LLVM IR with Tapir in it by passing the additional flag ftapir equals none in addition to the more standard -s-emit LLVM. If you want to, you can pull out your laptops and start building everything, but I won't assume that you're going to build a new version of LLVM from source in the time we have remaining. So I'll simply show you what's in this tutorial. So as mentioned, we're going to take the Kaleidoscope language, which is used as the tutorial language for LLVM, and we're going to introduce parallelism into it. We're actually going to pick up from a fairly late stage of the Kaleidoscope tutorial. This is basically after chapter 7. And at this point in the tutorial, the Kaleidoscope language supports a variety of features, including functions, as we see on the left, conditionals, loops, custom binary operators. There's an example of one at the very top in the code snippet, as well as variables. You can declare variables and treat them as memory in this particular version of Kaleidoscope. So that's going to be our starting point. And what we're going to do is we're going to add 3 familiar-looking keywords, spawn, sync, and par4, to Kaleidoscope. And with those changes, you'll be able to write the parallel Kaleidoscope code shown on the right. The top fib subroutine is a parallel implementation of fib in Kaleidoscope with these new constructs. And on the bottom, we have a simple code that uses parallel for loops. Now, if you want to follow along, either by coding things yourself or simply browsing the code, which is now on the web, you can find all of this code in the Tapir LLVM Git repository under the subdirectory examples, Kaleidoscope Tapir. To build and run the code, you want to invoke something like the following command. This is very similar to the standard Kaleidoscope command with a couple of changes, some of which were made honestly to fix bugs in the Kaleidoscope tutorial as of LLVM 8. But one of those changes introduces the Silk runtime system, the -L Silk RTS flag there. And as another note, you will need a copy of the Silk runtime system in the dynamic linkers library path in order to actually run the parallel Kaleidoscope code. But assuming you have all that, you'll be able to play around with this so-called toy example And there are some additional features that this code will allow. In particular, if you ever want to look at the parallel taper code generated for some Kaleidoscope code snippet, this particular code base supports the command line option, lower taper to none. Great. So in this tutorial, we're going to cover a few simple topics. First, I'm going to cover a couple of technical notes about the implementation of taper today, which is, and in particular, how it differs from the taper pseudocode we've seen thus far. We'll then see how to implement spawn and sync in Kaleidoscope. Then we'll move on to parallel loops. And finally, I want to close out this tutorial with a little puzzle. So first, some technical notes. The first thing you'll notice, if you take a look at the taper code that modern taper LLVM generates, you might notice that the sync instruction is in fact a terminator for a basic block. In previous examples in this slide deck, sync just appeared in the middle of a basic block. In fact, sync takes an additional argument, which is a destination basic block, and therefore sync terminates the basic block. Strictly speaking, this isn't a required part of taper's design. You could implement sync as a standalone instruction that just shows up in the middle of a basic block, but this turns out to facilitate a lot of program analyses. And the reason for that, intuitively, is that these taper constructs affect what instructions may execute in parallel with each other. And sync collapses some of that state. It says these instructions after the sync cannot execute in parallel with stuff before the sync. So it changes what's executing in parallel with what. And by making sync a terminator, we get a basic block boundary corresponding to that change in parallel state, if you will. So that helps out with a lot of LLVM passes. They don't have to scan through the content of a basic block to find a sync. They can just check the terminator and reason about what's going on based on those boundaries. Now, the other thing you'll notice is that there's a new concept in modern taper called the sync region. Taper instructions themselves, detach and reattach as shown here, as well as sync, the sync instruction itself, take an additional argument, which is called the sync region. And this argument is generated by a call to an LLVM intrinsic called sync region start. And basically, the semantics of a sync region are as follows. A sync within a given sync region will only ever wait on the computation spawned by detach instructions within the same sync region. So we see detach within a sync region, reattach within a sync region. In order for anything to wait on that detach, for a sync to wait on that detach, that sync has to be within the same sync region. We'll see a little bit more about why we need sync regions when we talk about parallel loops. But this is just another note of something you will see if you take a look at taper code directly. So those are the two technical notes. Everyone good so far? I see a lot of nods. Cool. Like 60% of the audience is nodding, so that's great.
Is the sync region syntactically identified?
Is a sync region syntactically identified? The sync region is defined by this SSA variable, in this case called syncreg, which is created by a call to this intrinsic and then used in several cases, used in the taper instructions. Basically, it's just a name. The sync region start intrinsic doesn't translate to anything. It's really just a placeholder. So there is an explicit representation of sync regions within the IR in order to keep track of what's going on. But it's otherwise just a placeholder to maintain some piece of state. Does that make some sense? Like they actually look like this. Does that sound good?
Go ahead.
Okay. So let's look at spawn and sync in Kaleidoscope. So at a high level, if we want to add these spawn and sync constructs to Kaleidoscope, it'll involve making the following high-level changes. We'll need to introduce some new tokens for the spawn and sync. We'll need expressions within the abstract syntax tree. We'll need to be able to parse the Kaleidoscope code with spawn and sync, and so we need routines for that. Honestly, all of that stuff is pretty standard boilerplate for whatever you need to do to add a new linguistic construct to any language. And so we're not going to focus on that here. What we're mostly going to focus on is the part that actually involves Tapir, namely the code gen step for these spawn and sync expressions within Kaleidoscope. Now the sync expression is actually really easy to code generate. The spawn expression is a bit more interesting. So here's the high-level overview of how code generation works for spawn. We start by creating a sync region for the spawned task, or we can choose to reuse an existing sync region. And then when we get to the actual spawn expression itself, we sandwich the spawned expression between a detach and a reattach. That detach-reattach pair denotes the creation of the parallel task and the returning from that parallel task, conceptually. As an important note, in order for the detach and the reattach to be associated with each other properly, they need to be within the same sync region, and they need to have the same continuation block. So in this case, the SR identifies the sync region, and that's the same for the detach and the reattach. And the final basic block destination, cont in this case, is the same for both the detach and the reattach. So that's all it takes to really code generate. Let me show you very quickly what that ends up looking like in terms of the Kaleidoscope code itself. Here we have the spawn expert AST code gen routine, and we can see it basically follows the same sequence of steps. We start off by acquiring a sync region for this particular detach, and we set that here. We get the current function. We then create some new basic blocks, one for the entry point of the detached task, and one for the continuation. We're going to need both of them in order to co-generate the detach and the reattach. We create the detach instruction wherever we are currently, passing it the sync region as well as the detach block and the continuation block. We set the insertion point to that detach block, and then we go ahead and emit the spawn subcomputation. This is a helper RAII in order to designate a new scope, if you will, that helps with certain code gen features, in particular managing sync regions as well as something else, as we'll see. We then generate the spawned subcomputation, just recursively invoking its code gen routine. If something fails, then it fails. Otherwise, we go ahead and we emit a reattach to the continuation block within the same sync region. To generate nice-looking LLVM IR, we push that continuation block onto the end of the function. We set that as our new insertion point, and we have a default return value for this whole statement of 0. And that's it. And of spawn and sync, that's honestly the more complicated one. The sync expression code gen is even simpler. We get a sync region for the sync. Wherever we are, we insert, we create a new basic block for the destination of the sync. Wherever we are, we generate the sync statement. We set the insertion point to its destination, and we're done. So that's all there is to it. And just like that, you have spawn and sync within Kaleidoscope. Now that's all good and fun. You now have new parallel constructs, but presumably you want them to actually execute code in parallel. Otherwise, that was wasted work, if you will. So in order to generate parallel executables, what needs to happen is that these Tapir constructs need to be translated into calls into some parallel runtime system. And to support that so-called lowering step, there are a couple of LLVM passes within Tapir itself. The lower Tapir to target pass does most of the heavy lifting of transforming Tapir constructs into these calls into some parallel runtime system. Now, it has the ability to target multiple parallel runtime systems. The parallel runtime system target is specified as part of target library info, along with a bunch of other parameters regarding machine code generation. And for this tutorial, we'll go ahead and stick with the Silk Plus runtime system target for Tapir. But yes, you can build new backends, new parallel runtime system backends for this lowering process by implementing the appropriate API within Tapir LLVM. I won't go through that today. If you have questions, I'd be delighted to hear them. So that's just a high-level overview of what it takes to generate that parallel runtime system code. I'll show you some of that code a little bit later on once we talk about parallel loops. But this is the high-level overview. Great. So we've added spawn and sync. We can parse them in our language. We can generate code for them. Let's give it a try. And now I'm going to do something which is risky for any presenter. I'm going to try to code on the fly while looking that way. Unless, by some luck, oh, yes, I can. Great. Okay. Good. Okay, so that was the code. And if I'm, yeah, good. So what we want to do is that. And if I set this up correctly, should have, to speed up typing just a little bit, I have the actual code I want to compile, the actual Kaleidoscope code I want to compile and run, handy right here. So this is a binary operator for sequencing two operations. This comes straight from the Kaleidoscope tutorial. It's a pretty boring function, but it'll do nicely for our purposes. Here is our parallel fib subroutine on a single line. Unfortunately, it is on a single line. So if n is less than 3, then we consider that a base case and we return 1. Otherwise, we create two new variables, x and y, and we use them in the following subcomputation. The first part spawns the computation x equals fib of n minus 1. That's sequenced with y equals fib of n minus 2. That's sequenced with a sync statement, which will wait for the spawn subcomputation. And finally, we return x plus y. Now, this ends up generating a bunch of code. A lot of this is parallel runtime calls. I can show you what the actual Tapir code looks like if you're curious. Just raise your hand and say, I'm curious about the Tapir code. But first, let's see if this works. Fib 45 takes a little while, but not too long in parallel. There we go. I also went ahead and added timers, so it will report some timing measurements whenever you actually execute some Kaleidoscope code. And here we can see that our fib of 45 routine ended up taking only just shy of 4 seconds while clock time, whereas the user time was much higher because it's using parallel processors. I can show you what it looks like for serial fib, or I can show you the parallel Tapir code, any special requests.
Can we see the Tapir code?
Yeah, sure. So for that, there's kind of a hacky way to do it, but there's a, I'm going to manually change the lowering target to none, which means it will just give us the Tapir code directly. Then I very carefully copy paste this, give me the same sequencing operator and this thing. And so what we have here is our fib subroutine with Tapir in it. So we create our sync region here. We create the x variable. This is after optimizations, by the way. So it actually code generates more and then cleans it up. But we have our sync region. We have a memory location for x, the return value of the spawn computation. We do our check for the base case. And if we fail that check, then we go ahead and execute the body, which initializes x to 0 and then spawns off the detached subcomputation, which computes fib of n minus 1, or sorry, computes n minus 1, calls fib on that, stores the result into x, and then does the reattach. The detach and reattach allow this code to execute in parallel with the continuation basic block, which computes n-2, calls fib on that result, and then sequences that code with the sync call later. Once we pass the sync, we know that the detach subcomputation has completed, so we can go ahead and read x out of its memory location, add it together with the return value of fib of n-2, which here is call times 6. And then we branch to the final basic block, which either takes 1, the return value of the base case, or whatever value we just computed, and it just returns that, which in the case of fib of 45 is some big number. And I think, because we're not targeting any runtime system, this will actually run serially. So it should take a little bit longer, but hopefully not too much longer. Longer enough for me to get a drink of water.
While that's, I guess, finished,
Mhm.
are you able to get the Tapir CFG output? Do you have
Can I get the Tapir CFG
a
output?
representation of it, like a dot file or anything?
So the Kaleidoscope REPL doesn't have a convenient way to do that, but the Clang, or sorry, not Clang, opt is perfectly capable of emitting that dot file. And we've used it from time to time, but yeah, it's kind of handy. There's probably a way to clean it up to show, like, oh, this is the detach edge and this is the reattach edge, and annotate it really nicely, but as is, you get a graphical representation of the CFG, and it looks pretty good. Cool. Sound good? Great. We can compute exponential time recursive Fibonacci in parallel with Kaleidoscope. Our lives are vastly improved by this experience. Okay, let's talk about another very common parallel construct, parallel loops. How do we go about adding parallel loops to Kaleidoscope? Now, I'll preface this discussion by saying parallel loops in Kaleidoscope end up being kind of a silly construct because there aren't that many uses of a parallel loop in a language that doesn't have arrays, and Kaleidoscope doesn't have arrays. But that's not the point of this tutorial. The point of the tutorial is to show off how you would actually do this thing using Tapir, and Kaleidoscope is good enough for that purpose. So let's dive right in. If we want to add parallel loops to Kaleidoscope, note that the language already has serial loops, so we can base a lot of what we're doing off of the code for handling serial loops. We still have to deal with a lot of the boilerplate stuff. Whenever we add a new language construct, we need a new token for the par4, some representation of the par4 in the abstract syntax tree, some code to parse that. And I'm not going to go through that today because that's standard language extension stuff. Don't get me wrong, there's a lot of interesting material in that space. It just doesn't really involve Tapir, so we're going to focus on the Tapir parts for today. And those Tapir parts show up when we implement the code gen routine for our par4 expression in the abstract syntax tree. Now we can base a lot of this on how code generation works for the ordinary serial for loop. And here I'm just diagramming things to keep the picture a little bit cleaner and simpler. So on the left we have a mock-up CFG that's generated for a serial for loop in Kaleidoscope. And as we see, we create a local variable allocation. We initialize it with the start expression of the for loop. We then have a basic block with multiple incoming edges that evaluates the exit condition and either executes the loop body or jumps past the loop altogether, depending on whether the outcome of the exit test. The loop body recursively contains some code. Maybe it's a simple bit of arithmetic. Maybe it's another loop. Maybe it's spawn and sync. Who knows? Once we complete the loop body, we go ahead and increment the induction variable var using the step expression, which, if unspecified, defaults to 1. And then we branch back to the head of the loop, and that gives us our back edge, thus creating the loop in the CFG. The parallel for loop code generation looks very similar. The only major differences are those highlighted on the slide, or at least this is a good place to start. We need a sync region for the parallel loop, so we create one up here. The body of the loop, rather than simply being in that basic block, will end up being detached using a pair of detach and reattach, which have the same destination, which is the increment block, as well as the same sync region. We mentioned both of those invariants before. And finally, once we finish the loop, we probably want to guarantee that all the parallel loop iterations are done. And the way that we wait on all those parallel loop iterations is by using a sync. So we insert a sync after the loop to wait on all those parallel loop iterations, make sure those complete before we move on past. So this will allow all the loop iterations to execute in parallel, but ensure that they're complete when we return. Now that we have parallel loops, we can talk about why we needed those sync regions in the first place. What happens if we start writing code that involves spawns and syncs as well as parallel loops in some form or another? For example, I could write a piece of code that spawns off some computation and then in the continuation does a parallel loop. If we don't have sync regions and we just have an ordinary sync, then what happens is that the sync will wait on all spawned computations within the function, or within the nested task, as it turns out. And so the sync will certainly wait on all the parallel loop iterations. That part's fine. But in this case, without the sync region, it'll also wait on the spawned task from before. And we don't necessarily want that behavior. That, in fact, serializes the computation. Everything is still correct. The code still generates a correct result, assuming you wrote correct code in the first place. But it's not as parallel as we may want. So the way that we can address this issue is by introducing the concept of sync regions and by making sure that the sync region for the parallel loop is distinct from the sync region for the spawned task before it. That make sense? So that's why we had sync regions. Originally, when we created Tapir, we didn't have sync regions. That's why it's not mentioned in any of the earlier slides. And that led to some interesting problems when you get a lot of inlining. It turns out that this kind of scenario in our test suite didn't arise pretty much at all. There might have been one or two cases where it came up. But nevertheless, we know that in principle it could occur. And so we had to extend the language with this new concept in order to accommodate it. But it's a pretty lightweight concept. It provides a very simple binding, if you will, between detaches and syncs. A lot leaner than any edges between detaches and their syncs. And so it works well for this purpose. Any questions about that? Cool. Hopefully that allows sync regions to make a bit more sense. Now I did say something about lowering Tapir instructions for spawn and sync to a parallel runtime system. We need to do something similar for parallel loops. The same lowering process works just fine on parallel loops. But if you actually take a look at the parallel loop construct, as we see here, and you think about what this means, this is a loop in which we step through each iteration, and for each iteration, we spawn off the computation of the body. So we spawn off iteration 0, and then spawn off iteration 1, and then spawn off iteration 2, and so on and so forth, until we reach the end of the loop, wherever that may be. If you think about what's involved, like how parallel is that computation, it turns out that that computation isn't terribly parallel. So that parallel loop representation isn't in and of itself particularly efficient or scalable. However, we like it a lot for optimization passes because it's very similar to a serial loop. And it makes it easy for LLVM optimizations that target serial loops to now target parallel loops and optimize them similarly. But ultimately, when we generate parallel code, we want to generate something that is efficient and scalable. And so we added an extra pass to the Tapir lowering process called loop spawning TI the moment, which does this transformation on parallel loops to transform them from this form where you spawn off each iteration in sequence to something where you do recursive divide and conquer over the space of iterations. You spawn off the first half of the iterations, you recursively do the second half, so on and so forth. And that gives you a much more efficient and scalable execution of the parallel loops. Now, the loop spawning TI pass is pretty sophisticated, and it requires a lot of other LLVM passes to run in order to perform necessary setup and cleanup. It's actually not, well, yeah. And you can see an example of that in the taper lowering passes, add taper lowering passes routine within the toy code, which I will show you right now. Hooray. Yeah, so here, so down here is where we actually create the loop spawning TI pass, and that does this transformation on parallel loops, assuming we haven't disabled lowering. And all of this is set up. Conceptually, what this is doing is it's canonicalizing the form of the loop. It's canonicalizing the representation of the induction variables. It's performing various forms of cleanup. And that just makes it much, much easier for this loop spawning pass to do the heavy lifting of this transformation. Turns out that the lower taper to target pass also needs some cleanup afterwards, but that's far simpler. We just ask it to clean up the CFG, and that's that. And we do the same for the loop spawning pass as well. So that's an example of the setup and cleanup. And by decomposing it into the heavy lifting of the loop spawning pass and leaving the setup and cleanup to the other passes, we get to reuse all of that carefully engineered and regularly maintained code within LLVM already, which is why we like that design. One other note, there are some technical reasons why this is the case, but the loop spawning TI pass turns out only runs on loops that are marked with appropriate metadata. And so when you're looking at the toy code, there is a step that inserts metadata when you're code generating parallel loops. And I'll show you the code to generate parallel loops in a bit, but I first want to show you a little puzzle. And in order to talk about the puzzle, I need to introduce the concept of race bugs. So parallel programming is strictly harder than serial programming because of a particular kind of bug that arises in parallel programs called a race bug. Let's take a look at some simple Silk code to demonstrate what a race bug looks like. You've probably seen this kind of bug before, and this buggy norm routine, in fact, exhibits one such race bug. Here we're having the parallel loop iterations in the Silk for loop all update the exact same sum variable. And so we're performing concurrent updates to sum. As they often talk about in early parallel programming courses, this leads to concurrent updates which are not controlled and therefore produce non-deterministic behavior. Now that's all fine and good. If we stare at this norm routine for a couple of minutes, we can, and I tell you that there's a race bug in it, you can probably find it. But race bugs are notoriously hard to debug for a variety of reasons. For example, if you're dealing with a much larger code base, you may run that code base a lot of times and never see the race bug. So how do you find a race bug if you get really quote-unquote lucky and never actually see different results? Maybe there isn't a bug, or maybe things are just working out really well for you. And moreover, if your code base is longer than 4 lines, let's say it's 500,000 lines or 1 million lines, how exactly do you spot these bugs? How do you identify them and let alone figure out how to fix them? Now, with all this work on Tapir and introducing parallelism into the compiler, we actually opened the door for a brand new kind of bug, a brand new kind of issue with race bugs. Namely, now it can be the compiler's fault. Now we could write perfectly bug-free code, but have a bug in the compiler that introduces a race into our code. So here's the puzzle. You should have seen this coming, honestly. There's a race in this code, in particular in the generated code for the parallel for loop. Who can tell me where it is? If you like, I can walk through how this code works. It's similar to the code gen we saw earlier, but yep. It's a pretty small parallel loop. Pretty small loop. Any questions about this code so far? Sorry? You look like you want to say something.
No, I mean,
All right, so let's walk through this really quickly. We have ourselves a parallel for loop with an induction variable I. And when we code generate this, we first generate I as a memory location. That's what the alloca does initially. We set the value of I to 0 by storing the value 0 into I. That's what the star I equals 0 does. Then we branch into the loop itself, and that tests the exit condition, namely, if I load I and compare that to n, is I smaller than n? If so, go ahead and execute the loop. If not, exit the loop and perform the sync. When we execute the loop, we perform a detach, which allows the body to execute in parallel. So the body of that loop, which loads the value of I and calls bar on that, that's going to happen in parallel with the other iterations of the loop. And if we see the continuation, that loads the value of I, adds 1 to it, and stores that value back into I, and branches back to the beginning of the loop. So where's the bug?
is it when you load the I in the bar call,
When you load the I in the bar call, that's one endpoint of the bug.
and then incrementing I below it?
Exactly. We need 2 endpoints for any race bug. And in this case, those endpoints end up being 2 different lines of code. That doesn't always happen, but we're lucky in this case. The load of the induction variable I here, which we pass to the call to bar, can happen in parallel with the update to the induction variable in the step for the loop. So this was a problem that arose purely from how we generated the code for the parallel loop. So code generation for parallel loops is a bit more complicated than that for serial loops because of issues like this. And I've encountered this bug many, many times when code generating parallel loops in a bunch of different contexts. So it's a fun one. I thought I would share it. So how would we go about fixing this race? Any thoughts before I show you the answer on the next slide?
Try to test it a whole bunch, and then try to run it in serial and see if your results match.
So that would help us find the bug, but how do we fix the bug?
Without introducing other constructs like locks or these kind of things.
Yeah, we don't need new constructs here.
Do something to make sure. Let's see.
All right, so with Tapir's representation, there's a pretty easy way to fix this bug. And the key is going to be moving the actual allocation of the induction variable that we use inside of the loop body and performing that allocation within the loop body itself. So on the left, we have the original parallel for loop, which I showed you on the previous slide. The deletions are highlighted in red, and the new additions to the code generation for the parallel for loop are shown on the right in green. So what we're doing here is we're using an ordinary SSA value for the loop control. And we're just going to, because that's an SSA value, essentially that gets passed by value to the loop body on each iteration. And then in order to use that induction variable, since we're just code generating some body and we don't know how it's going to access the variable, we'll go ahead and do an allocation within the parallel loop body and store that SSA value in there. And that will be enough for us to resolve this race. So the key here is moving that allocation into the body of the loop. And in other words, making sure that the variable that's used within the task scope has allocated memory for it within the task itself, rather than in the parent. That makes some sense? All right, cool.
So how does it get assigned to value?
Sorry?
How does the variable I, which is allocated within the loop, get assigned a value?
How does I get assigned a value? So what we're doing in this case, for the loop control on the outside, let me remove that for a second. We have the condition at the top, which is just maintaining an SSA value I0. So conceptually, that's a register. And the value of I0 is going to be 0 when you come from the entry block, and it's going to be the value of some other SSA register, I1, if you're following the back edge. We'll do all the loop control using that SSA value, I0. But when we enter the loop body, we'll just pass that SSA value by value to the loop body. So we can keep track of that. And after the allocation, we just store the value of I0 into the memory location for the locally allocated I. And because we're going to, one way you can think about this, we're going to execute this loop body a bunch of times in parallel. Each one of those will be its own task scope. So each one of those can have its own local stack, and it can do local allocations within that stack. Those will all happen independently of any other allocations happening in other parallel iterations. Everyone good? Cool. Now this is actually illustrative of a pretty common pattern when it comes to Tapir code. Whenever you have spawns and sinks and parallel for loops, and those spawn computations could be using local variables, it's important to make sure that the compiler code generates things properly, and in particular that it generates allocations for those local variables within the scope of the task that uses them. And it turns out that the same kind of pattern should be adopted for the creation of sync regions. So whenever you nest parallelism, you have detaches within spawn tasks, or you have nested parallel for loops, you want to allocate sync regions within the appropriate task. Now this bug also illustrates one of the big problems when it comes to dealing with Tapir, namely how do you debug it? It's a parallel compiler, it's generating parallel code. The errors in what it generates are parallel errors, and this is basically a compiler writer's worst nightmare. You could imagine that you're developing a compiler, you're working really late at night, and suddenly you see a bug report come in where some angry hacker attaches a piece of code and says, hey, my parallel code is perfectly fine and race-free. It's your compiler that's putting a race in it, angry emoji. And so you begrudgingly open up this code and you run it once and everything's fine. And then you run it 10 more times and everything's fine. And then you run it 1,000 more times and everything's fine. So despite this programmer's assertion, multiple runs of this program indicate no problem whatsoever. And you're left with the following question. Is the compiler actually buggy, or is this angry hacker just wrong? Now, there are other race detectors out there. For example, threat sanitizer is basically built into the LLVM compiler today. There are also state-of-the-art race detectors that have arisen from academic work, such as FastTrack. The issue with these efficient race detectors is that they don't quite work for Tapir, because these detectors are best effort. They don't offer any guarantees to find a race if one exists, even in a parallel execution of the program. These detectors, in addition, are designed to handle just a few parallel threads that are executing, where the number of threads is comparable to the number of processors on the system. You can think of this as handling p-threaded codes or server-client codes. But task parallel languages such as Silk are fundamentally designed to get parallel speedup by exposing orders of magnitude more parallel tasks than there are processors on the system. You overwhelm the system with parallel tasks, and now the processors have a lot of freedom in choosing what they want to execute, and that allows them to schedule and load balance extremely effectively. Unfortunately, that inhibits the effectiveness of existing race detectors like threat sanitizer. Now, the good news is that with Tapir, we actually incorporated our own race detector called SilkSan, which is a provably good non-determinism detector that can verify the existence of race bugs in a deterministic fashion. So what SilkSan does is that you give it a program and an input. It's a dynamic race detector. So you give it a program and input, or alternatively, a regression test. And you run it with SilkSan on, and SilkSan is guaranteed to either find a race if one exists, or certify that there are no races in this program. SilkSan's algorithm is efficient. It introduces approximately constant overhead compared to the ordinary serial execution of the program. And SilkSan has been invaluable in our efforts to develop Tapir. We've used SilkSan. We were originally developing Tapir LLVM in conjunction with opt to pinpoint optimization passes that were introducing races. And more recently, we used SilkSan, with Daniela's help, we used SilkSan to debug Tapir code generation in Tapir XLA, specifically related to stack allocations. Like I said, I've seen that race bug before. That's why I chose to show you. Now, it turns out that we can actually use SilkSan on our Kaleidoscope code. So the last bit of demo that I want to show you is just using SilkSan in that fashion. So you have to compile Kaleidoscope in a slightly different way. I've already gone ahead and done that. In particular, you have to link in the SilkSan library, which is compiled as part of Tapir LLVM and Tapir Clang, but it takes some finding in order to discover it. And then you can use SilkSan to check your code. And in fact, we're going to use SilkSan to detect that race bug that we saw before, at least to detect it. Now, it turns out that with this particular race bug, you have to disable optimizations in order to actually see the race bug, because otherwise the optimizer, even the simplest optimizations, will get rid of the race bug and give you deterministic behavior, which is also really fun. But we'll go ahead and disable optimizations. And let's pull up. Let's first just drop some somewhat interesting code in place. And then I'm going to put in a really simple parallel for loop that looks structurally similar to what we saw before. So we have a subroutine here, foo, which takes an input n, and it does a parallel for loop from I equals 0 up to n, and it's just going to call fib of I. And assuming that I compiled this correctly before, whoops, that's not what I wanted. There it goes. We run foo of 10. So we've got 10 parallel iterations, and lo and behold, we see that SilkSan runs and it detects a race at a particular address, and this race involves reads and writes to the variable I, which, lo and behold, well, it's off the screen now, but that was the code we had before, and indeed I is our induction variable. So we can use SilkSan to identify this code generation bug. That was a lot easier than staring at a CFG for a while. Even a relatively tame, cleaned up CFG. That's pretty nice. I just want to wrap up by saying a couple more words about races. So races, it turns out, well, specifically determinacy races, turn out to be integral to Tapir's formal semantics, as we've more recently discovered. So when I say determinacy race, all I'm referring to is a situation where you have two logically parallel instructions that access the same memory location, and at least one of those accesses performs a write to the location. So here, the updates to the sum variable do constitute a determinacy race. Now, determinacy races, by this definition, differ from the more standard definition of data races, which also require this condition, but additionally consider the locks or atomicity guarantees that you have on those parallel accesses. So here we're just regarding situations where you have parallel accesses. Data races introduce additional semantics on top of that. Now the nice thing about Tapir is that we have determinacy race detection built into its semantics, and we can actually show the following theorem, that if a Tapir program, in fact, contains no determinacy races, then semantically speaking, it's equivalent to a serial projection. Every execution of the Tapir program will produce the same behavior as the serial projection of that program. And that's a really powerful feature that allows compilers to analyze and optimize deterministic Tapir parallel programs by reasoning very similarly about ordinary serial programs, and in particular by reasoning about their serial projection. Now, this correspondence to the serial projection does mean that Tapir looks at a special corner of parallel programming. And if you go to any parallel computing conference and you look at the set of topics that they discuss, it's pretty broad, honestly. You'll get talks about p-threads and message passing. You'll get talks about vectorization and task parallelism and data parallelism. You'll see talks on data flow or multi-core, HPC and GPUs, heterogeneous computing, shared memory or distributed memory, clients and servers, races and locks, concurrency, memory models, scheduling, work efficiency, parallel speedup, and the list just goes on and on. And I have to admit that although Tapir deals with some of this, Tapir does not directly address all of these concepts in parallel programming. The focus of Tapir may be useful in many of these contexts, but the focus of Tapir is that it strives to make it easy for average programmers to write efficient programs that achieve parallel speedup. And so that means focus on multi-cores and task parallelism, a simple and extensible model of parallel computing that allows for deterministic debugging, serial semantics, a simple execution model, work efficiency, as we saw before, but parallel speedup nonetheless, composable performance. If I were to run multiple parallel subcomputations together, I expect the speedup to scale in a certain way and those parallel computations not to interfere. And finally, Tapir focuses on parallelism as opposed to concurrency. And based on this work, we see that Tapir adds one more thing to the list of advantages of task parallel programming. Task parallelism facilitates parallel programming and performance engineering because it allows programmers to write many parallel programs as deterministic parallel programs, thus freeing them from having to worry about concurrency. Task parallel programming also admits provably effective algorithms for detecting determinacy races, as we've seen with Silksand. Task parallel codes can exhibit composable parallel performance, as I mentioned before, allowing them to be easily incorporated into larger programs. That allows us to incorporate Tapir parallelism into something as complicated as TensorFlow. And moreover, Tapir shows how compilers can optimize task parallel programs similarly to serial programs. So just to wrap up, I know I'm running over time. Quick overview of the status of Tapir. You can try out Tapir yourself. The code is available on GitHub. The instructions for how to download it and build it can be found on silk.mit.edu. We've been engineering the Tapir codebase for a while now, and at this point, It's been battle tested by roughly 200 undergraduates and graduate students over 3 semesters at MIT and CMU, and apparently Washington University in St. Louis. Tapir LLVM and its Silk Clang frontend are largely compatible with Silk Plus, and they achieve comparable or better performance versus the Silk Plus implementations in GCC, ICC, and LLVM. We've also incorporated a variety of tools into Tapir LLVM, including a non-determinism detector, a scalability analyzer, and an instrumentation framework, which I believe Danielle will talk about next week. And that allows for building fast dynamic analysis tools. And we're continuing to maintain and enhance this code base as part of our ongoing Open Silk effort. There have been several groups that have started using Tapir in various interesting ways. This is a abbreviated list. Billy Moses, along with a couple of former UROPs and MEnges, looked at extending Halide and LLVM's Poly project to incorporate Tapir. Several folks at the National Labs worked with Billy to build a prototype front-end and back-end to Tapir for handling OpenMP tasks. Valentin Chiravi, who actually sits just down the hall from me, is currently working on building a Julia front-end for Tapir LLVM. EMU Technology in New York is working on a back-end for Tapir that targets their custom in-memory processing hardware. And I've heard from a couple other people about interesting ways that they've incorporated Tapir. I know I'm running over time, but that's all I have to say about Tapir. Thank you all for listening. Be happy to take any questions.
Take some questions offline.
Sure. Sounds good to me. Thank you all again.